Hi there students, we're going to talk about the heating and cooling graph of naphthalene. Now this always comes out on paper too, so just listen to me and you will get this very straightforward. Okay, let's start with the heating graph of naphthalene or the heating curve of naphthalene. Okay, so what we have is, since it's a curve, we're going to have an x and a y axis. So okay, sorry about my lines. X-axis is time, and this is always in minutes, and your y-axis is going to be temperature. Okay, and this will be in degrees Celsius. Okay, so now heating curve of naphthalene, let's think about this logically. We're heating naphthalene. Naphthalene is now a solid. We heat it. What happens? It becomes a liquid. We further heat it, it becomes a gas. If it's currently a solid, because that's what we're starting with, is the temperature going to be high or is the temperature going to be low? Logically, it's going to be low, right? Exactly. So we start off over here. Now, the temperature increases. So as time progresses, so graph goes like this. Now, what happens? The graph flattens out. Why does the graph flatten out? Because this is where the phase change occurs. This is where solid naphthalene becomes a liquid. Once it becomes a liquid, the temperature further increases. And then what happens? The graph flattens out. What happens when the graph flattens out? Liquid naphthalene becomes gas naphthalene. And then the temperature further increases. Now quickly I'm going to write down some things, students. The melting point. Now from the last chapter we learned that, or the last lesson, we learned that the melting point is the temperature at which a solid becomes a liquid at a constant pressure, correct? Now this is not always the case, but just know this figure. The melting point of naphthalene is 79 to 80 degrees Celsius. Okay. Now I'm going to explain this graph to you. We start off here. It's a naphthalene is a solid. Temperature increases as time goes on. Is naphthalene a liquid over here? No. All that happens from this point to this point is a temperature increase. The phase is still a solid. Now, what about this line? At this line, the solid is at a constant temperature. The temperature is not increasing. What is happening? The bonds of the solid are being broken. The heat energy applied is used to break the bonds, and what happens when the bonds break? The particles move apart. So at this stage, the solid becomes a liquid. When does it exactly become a liquid? It becomes a liquid at the end of this process. So at the end of this line, naphthalene is now a liquid at this point. Now temperature further increases. Does naphthalene become a gas yet? Not yet, students. It reaches this temperature, and then at this point you have a constant temperature, a flat line. So again, the bonds are being broken, heat energy is absorbed, and at this point, this last point over here, naphthalene becomes a gas. Okay, so some of the questions that they like to ask on this is, what happens? Okay, what happens at certain points of the graph? So I'm going to call this point A, this point B, this point C, this point D, and the last one is going to be E. Okay, so what happens quickly from A to B? The temperature increases, the particles absorb energy, they vibrate faster, kinetic energy increases, all these good things happen. Now at point B, naphthalene is still a solid. When does it become a liquid? It becomes a liquid at point C. What's the transition from B to C? The naphthalene is continuously being heated, and now this is the key word, guys. They like to ask, why is the temperature constant? Why constant temperature at BC? Now the reason, as I mentioned to you, was that the heat absorbed, because naphthalene is absorbing heat at this point, is used to overcome force of attraction between particles. Force of attraction between particles. Now, what does this mean in simple English? It means that at this line, heat energy is being absorbed. The naphthalene is gaining heat. The temperature is constant, but it's still being heated, right? So when heat is supplied, the bonds break. When the bonds break, the particles are no longer close to each other. So the force of attraction decreases. Does that make sense, students? Awesome. I knew it would. So what about line CD? The temperature just increases. No phase change. The phase change occurs here. The reason? The same thing. Heat absorbed for naphthalene to overcome the force of attraction between the particles. And at point E, naphthalene becomes a gas. That's it. Straightforward. Now, one more thing they like to ask is, why is there a water bath? So for this particular experiment, they like to use a water bath. Okay. The reason? Now, I told you that the boiling, we know the melting point of naphthalene is 79 to 80 degrees Celsius. Well, guess what? The boiling point of water is higher than this. The boiling point of water is 100 degrees Celsius. So the reason we use a water bath is to ensure uniform heating. Okay. We basically place the naphthalene in a naphthalene and its and the container of the naphthalene into a water bath, so that there is uniform heating, because the temperature or the boiling point of the water bath is more than that of the naphthalene. So that's it, guys. Straightforward. Okay, temperature increase from A to B, solid becomes liquid at point C. Temperature increase from C to D, naphthalene becomes a gas at point E. Why is there constant temperature at BC and DE? Because the heat absorbed is used to overcome force of attraction between particles. What is the melting point of naphthalene? About 79 to 80 degrees Celsius. Why do we use a water bath? To ensure uniform heating. That's it. We're done with the heating curve of naphthalene. Now let's look at the cooling curve of naphthalene. Okay. So very quickly, cooling curve of naphthalene is going to be almost the same thing, just slightly different, guys. Cooling curve of naphthalene. Now, what I'm going to do for this part is, I'm not going to write notes. I'm just going to draw it out and explain. We're going to do this together, okay, guys? For this session, just pretend that I'm taking SPM with you. If you do that, we study together, we all get A's, we all be happy. And just for your information, guys, I always made an A1 in SPM, so I know what I'm doing. Trust me, and I promise you, you'll be good. So cooling curve of naphthalene, again, x-axis time in minutes, y-axis temperature, Celsius. Okay, now let's think logically. We're cooling naphthalene. In the opposite scenario, we were heating naphthalene. Now we're cooling it. So obviously when you cool something, does the temperature increase or decrease? It decreases, right? Right now naphthalene is a gas. It has a high temperature. So we don't start over here. We start at the top. So we start at the top, temperature decreases, then temperature remains constant, and you may have guessed it, and you have probably guessed it right. This is where the phase change occurs. Then the temperature decreases. Now again the line goes constant, and the last part, temperature decreases. So again we just label this really quick: A, B, C, D and E. So I'll give you guys about 30 seconds to figure out what's going on. At the end of that, we talk about this, okay? Go, guys. Alright, guys, I'm gonna explain this to you now. So we start at this point. Over here, naphthalene is not a solid, it's a gas. Temperature decreases, you're cooling the naphthalene. Temperature decreases at this point. Does it become a liquid yet? Not yet. Now, temperature is constant. What happens when the temperature is constant? There's heat that is being, well, in this case we're not doing heat, right? We're decreasing the temperature, guys. So think about it for a second. How would you explain this? It is not, you cannot say heat absorbed is used to overcome force of attraction, because the naphthalene is not absorbing any heat, is it? So what we're going to say is the heat energy released. Okay, we don't talk about cooling, we just use the word heat. Instead of heat absorbed, we say heat released. So the heat released is used to form bonds. Okay, so I'll just write this down. Heat released, because we're decreasing the temperature, is used to, we're not forming bonds, we're not breaking bonds, sorry, we are forming bonds, opposite. So from here to here temperature decreases, here to here temperature is constant, the heat release is used to form bonds, and at this point naphthalene becomes a liquid. Then temperature decreases, and at this point temperature is constant, but there is still a reduction, like not to say heat, but there's a the heat released is used to form bonds. It's constant. So at this point, at this E over here, naphthalene becomes a solid, and that's it, guys. That's all there is for the cooling curve of naphthalene. One important thing to know for this is that in this for this particular experiment, we put the naphthalene or the liquid naphthalene into a conical flask. Okay, it's being cooled in a conical flask. Why does that happen? Why cool naphthalene in conical flask? Earlier on it was to ensure uniform heating, right? In this case, guess what it is? I'll just write it down. Come on, guys, guess. Think logically. It's always going to have the word uniform depending on the situation. If it's heating, it's uniform heating. If it's cooling, it's uniform cooling. That's it, guys. Straightforward. Really easy topic. It's always on SPM. I had it on my SPM. It took me about 5 minutes or so. We had to draw the graph. So remember, they'll give you some values. X-axis time in minutes, y-axis temperature in Celsius. You know how to explain the graph. Just keep watching the video. If you don't get it, let me know. Write a comment if you don't get anything. I'll be more than happy to explain it to you. Thanks, guys.